Hey there, welcome to part two of vectors. In this video, we're going to talk about, I already forgot, uh, unit vectors, how numbers interact with vectors, including scalars, what a unit vector is, and we might get into, if I don't go on too long, um, the dot product uh, and that part of it. So unit vectors, also adding vectors, forgot to mention that. Not multiplying vectors, but subtracting vectors, yes. So the vector, we already talked about it, is magnitude and direction, just like vector. If you can't remember what a vector is, just think about vector from Despicable Me. It's like magnitude and direction. He's he's crazy. Anyways, um, I forgot what I was going to talk about again. Oh yeah. So remember when I talked about scalars in the last video? A scalar is just a number, and this can be anything. It can be the magnitude of a different vector. It can be something else. So let's say you have a vector. Vector v. Just gonna name it vector v. Is, remember you have to use the angle brackets. Is going to be 3, 8. So remember that means 3, this is a change of 3 on the x-axis and a change of 8 on the y-axis from whichever point in time that you were starting in. And this can be at 0, 0, or this can be anywhere else. Now, this is technically the vector from 0, 0. Like, you start at 0, and you go 3, and then you go up 8. So if you start at 0, 0, then you can almost describe this as a coordinate. So if beginning point is 0, 0, end point is 3, 8. So this is kind of where we get into where I don't quite know perfectly what I'm talking about, but that's why I'm making these videos. So numbers can interact with vectors. Let's say I want to scale this vector up. Like, I don't want to do the vector once, I want to do it twice. Like, a real life example could be like, instead of walking a single mile, it's like, you know what, today I'm going to walk 2 miles. So I'm going to go twice as far as I did. But in the same direction, you got to understand that. This is kind of like Jesus from The Chosen carrying the Roman stuff. He's like, when someone gives you a cloak, you walk with them 20, no, not 20, I can't remember the saying. Anyways, and the apostles are like, this is stupid. But you go twice as far in the same direction. So we have 3, 8, and let's say I want to go twice as far. So vector twice, or vector times 2. And so think about it in your head. If I'm going to do this vector twice, if I'm going to go in this direction for this amount, well, not time, but for this distance twice, that means I'm not going to go 3, it means I'm going to go 6. I mean, another 3. So when you get to the end, it's 6. And for your y values, I'm not just going to go 8, I'm going to go another 8. 16. So if we went just here, this is vector v. This is vector v. But if we go twice as far, not to scale, we get 2v. Now these are both vector v, same direction, just v twice. So that's 2v. How do you write this? Well, or how do you actually do this math? It's just 2, there's 3, 8, angle bracket 8, which is equal to angle bracket 6, 16. So 16. It's as simple as that. That's how you multiply a vector. And I would draw your attention to the fact that it's just scaling the vector. Like, the word scalar refers to simple magnitudes, or just like this integer right here, it's just a number. So I've scaled up my vector. I've just done it twice. I can do it 3 times. I can do it 4 times. I can do it half times. I can go half of my vector. Keep in mind, it doesn't change the direction. It's just how far that vector goes. So that's how you multiply a scalar times a vector. Pretty simple. Now let's talk about how to add a vector, or add vectors, I think. I might have something else first. Nope, we're talking about the unit vector. No, we're going to talk about adding vectors first. The unit vector is kind of its own thing after that, building on what we've already learned. So, adding vectors. This one I'm going to get a bit graphical, not in a violent way, but you wish. Let's say we have two vectors. Vector, I was going to put an arrow on the end. I'm going to put an arrow here, but pretend that it just ends where the arrow ends. And I have another vector. So these are two vectors, vector A and vector B. These two vectors are just floating in space. They're not fixed. They're not on a coordinate plane right now. They're nowhere. They're just wherever they are. So like this distance right here, like it doesn't matter. It doesn't matter where they are, which means that I can take them and put them wherever I want to. I'm going to add vector A and B. Vector A plus vector B. So for that, we kind of have to assume that they're going to start in the same spot because they're going to act on each other. So for the sake of being able to add them, we're going to take B and we're going to move B to be right here. So think about it in your head. If someone is pulling on a box, we're going to get into like a physical example of this. If someone's pulling on a box, think back to your physics class, in this direction at a 45-degree angle, 45-degree angle from here, 45, and someone else is pulling on it from the side, just at like a 0-degree angle, which direction is that box going to go? It's not going to go sideways. It's not going to go straight up diagonally either. It's going to go kind of up the middle. Because, why? Two different forces are acting on it. It's going in two different directions at once. And so these directions are going to cancel out. And they're going to go in the midway point. And that's why we're going to add vectors. So, when you add vectors, what is the result of your addition? Your result is nothing more than the end coordinate of your vector. It's a new vector. I'm going to pretend it starts right there. These two vectors, like they start there and this one starts here, these two vectors combined are going to end up getting you here. Maybe not that far, but they're going to end up getting you there, and that's your new vector. Like, it's not much more than that. Like, how far on the x-axis are we actually going to go, and how far on the y-axis are we actually going to go? So here's an example using some numbers. Vector, not that. 5, 13, and let's think about one that goes like somewhere else. 3 and 9. So I'm going to draw these. I'm going to erase this box up here. Sorry, I almost music. That sounds autistic. So let's draw this on the graph, or just somewhere, not on a graph. We're just going to put it on a plane. This is going to be vector A, and this is going to be vector B. We are still adding vectors A and B. Vector A is 5, goes like over 5, and up 13, so that means kind of steep. And I just say it goes right there, and it ends like right there. 3, 9 is a vector that looks something like this. It goes over 3, but doesn't go quite as far. Actually, it's way steeper. It almost goes up. You know what, let's make this longer so it makes more sense. 10. So x is 10 now. So now it goes over and it goes kind of high. So we have these two vectors. This one goes 10 over and 9 up, and this one goes 5 over and 13 up. And so if I have these two vectors, how do I add them? Well, first, I just take them and I put them together. So I'm going to go over here. This is not a vector. I'll just do that, not a vector. And we do vector A, label these. Vector A goes up and like that. A, vector B goes something like this. And so you see, like, they're this long, but that's what it is. So if I have a box, like pretend there's a box here, or whatever it is, and I have these two vectors, what is going to happen if they are both moving? Well, we're going to get a new destination. This is the theory of adding a vector. It's just like if I have vector that one going there, how do they balance out? Adding vectors is just balancing vectors together. So uh, let's do the math. How do you think this is done? Well, it's essentially you're just going to combine the coordinates. So in a 5 and a 10, actually I think I need to look at my notes for this one. Give me a second.